Modern AI isn't just generating words, it's actively carving a canyon that it can never escape from. Welcome to the hidden trap of structural encoding. Have you ever stopped to wonder what actually happens when a system is pushed past the point of no return? Welcome to this explainer. You know, most of us share this common thought that when something exceeds its limits of endurance, it simply transitions to a new state or just breaks down entirely. But reality actually holds a much deeper and more fascinating mystery unfolding just beneath the surface of everything, from biology and physics to even the most advanced artificial intelligence systems we are building today. Today, we will deconstruct this mystery together to see how systems don't just react to stress, but actually remember and change their very identity completely invisibly. Let's start with a question that might sound a bit strange. What does bending a piece of metal until it permanently deforms have in common with a modern AI model like ChatGPT, which processes millions of data points every second? You're probably thinking these two things have nothing to do with each other, right? But surprisingly, at the deepest structural level, they follow the exact same mind-bending principle regarding limits. When you bend metal too far, it can never bounce back to its original shape. It is permanently altered. So what about AI? The answer lies in a groundbreaking principle. The threshold doesn't merely trigger a response. It encodes that very response deep into the structure of the system itself. This is truly a powerful idea. When a system encounters a critical regime boundary, it doesn't just snap back like a rubber ball. That encounter leaves permanent traces, hidden structures that we cannot easily see with the naked eye, but which play a decisive role in shaping the entire future of that system. Now let's dive into the first part, crossing thresholds. Let's visualize the core difference here. On one side, we have a temporary response. It's exactly like when you gently stretch a rubber band and let go. It returns to its original state without leaving any trace. On the other hand, we have what is called structural encoding. The encounter with the boundary this time completely alters how that system will respond in the future. This means that what just happened has been written directly into the system's dynamic DNA. The future paths that the system can take are now completely bent in a new direction. Moving on to part 2, structural memory. The idea of an invisible type of memory is actually present everywhere around us. In physics, it's called hysteresis. A bent metal bar will recover along a completely different path than the one along which it was deformed. In biology, it's immune memory. Your body learns how to deal with a virus after being exposed to it, and the structure of your immune system is permanently altered. Or in complex network systems, it's path dependence, where seemingly minor initial changes are enough to constrain future options. The repetition of this principle across all fields is strikingly clear. The key point that ties all of this together is the concept of structural memory. This is the exact moment when an event at a regime boundary turns into a new rule of operation. The system doesn't need a physical brain to remember. Its physical, biological, or mathematical structure itself has actually become that memory. So, how does this process take place? Let's move on to part 3, encoding mechanism. This is how the magic actually happens through 3 highly sequential steps. Step 1. Probability redistribution. Suddenly, certain responses become statistically more likely to happen, while others become harder to reach. Step 2. Channel formation through reinforcement. The system begins to prioritize certain pathways simply because they receive continuous positive feedback. And finally, step 3. Constraint reshaping. The system's ability to resist new changes has now been completely redefined. The landscape in which the system operates has now tilted heavily to one side. There is a perfect metaphor to illustrate this, just like water carving out paths through a landscape. Imagine a heavy rainfall pouring down on a hill. The water will automatically find the path of least resistance to flow down. The next time it rains, the water will continue to flow into that exact same groove, carving it a bit deeper. Repeating over and over again, a tiny stream will eventually become a massive canyon. Complex systems form reinforcement channels in the exact same way. Now let's look at part 4, observing encoding. How do we know a system is undergoing internal changes from the outside? We don't look for an explosion or a sudden crash. Instead, we must track the system's behavior over time through three very subtle warning signs. First is trajectory bias. The system always tends to favor responses in a consistent direction. Second is response asymmetry. The same input, but if applied from the left, the system recovers quickly. If applied from the right, the recovery is incredibly sluggish. And finally, reduced adaptability. The system's range of flexible responses becomes increasingly narrow and restricted. You know what? This trajectory bias is extremely dangerous. Initially, the options might be evenly distributed, but once the structure has been encoded by being pushed past its limits, a reinforced path can expand and capture up to 75% of the probability space. It acts exactly like a greedy monster swallowing up alternative solutions, squeezing other options down to a minimum. Bit by bit, the system loses its inherent flexibility, and this shift creates the greatest risk we need to worry about. We move from an elastic state, where the system is incredibly robust, flexible, and ready to respond to unexpected environmental changes, to a rigidity regime. In this rigid state, the system might look like it's still operating stably on the surface, but in reality, it has frozen into a few narrow pathways. Any major shock outside of its expectations can cause the entire system to collapse instantly, simply because it no longer has the capacity to adapt. Finally, we will connect everything together in Part 5, Counterforce. As you can see, the large language models or AI systems we use every day are by no means mindless machines following a rigid set of pre-written rules. Their behavior actually emerges from sequential probabilistic inference. They are constantly navigating and searching through a massive, multi-dimensional probability universe. Every single word that an AI generates alters the probability space for the next word. It is a perfectly dynamic and incredibly complex system, but it is precisely at this point that a vital warning emerges. Just like water carving out a canyon, AI also learns through reinforcement. Over time, frequently reinforced pathways become much easier to follow, while alternative trajectories become far less likely. If we simply let AI run on its own without control, this cumulative reinforcement will naturally push the AI model from a flexible, creative state into a deadly rigid regime. It will only output boilerplate, biased answers, and completely lose its ability to adapt to new innovations. And that brings us all to one of the most urgent and challenging questions in designing complex systems today. If reinforcement forces continuously narrow the operating trajectories, what structural mechanisms can be applied to maintain responsiveness within the system? Clearly, we need something called a structural counterforce, a balancing force that pushes back to keep the system in an elastic regime. Finding and designing this counterforce is the key to shaping the future of technology, because without it, our smartest systems will eventually become the most rigid crones. What do you think about this? Thank you for watching today's explainer, and always keep your own thinking highly elastic. See you next time.